Hello, my name is Ken Watts. I'm a PhD student in the Advanced Communication Networks Laboratory in the Department of Electrical and Computer Engineering at UMASS Lowell. My talk is titled Towards Securing Cyber-Physical Power Systems. With cyber attacks on the rise, it is important to be proactive in identifying threats to communication networks and protecting critical infrastructure. In the recent past, there have been several high-profile attacks of this nature. In 2007, Estonia dealt with a series of disruptive cyber attacks. In 2010, Stuxnet was responsible for sabotaging Iranian centrifuges. And in 2015, Ukraine experienced a cyber attack on one of their power grids. Smart grids, which may incorporate Internet of Things technology, can be vulnerable to cyber attacks. Additionally, cyber attacks on energy infrastructures have been increasing. Considering all of this, securing critical infrastructure to include smart grids has never been more important. In order to better understand when a cyber attack is underway, ideally we can use a data set that contains both standard or benign network data as well as malicious attack data. CIC-IDS 2017 is a data set created by the Canadian Institute for Cybersecurity that is widely used for training machine learning algorithms to recognize when a cyber attack is underway. This data set is composed of a mix between benign and attack data flows and spans a set of 72 distinct features. TIC Flow Meter is a software tool used to extract TCP data flows from captured network data stored in PCAP files or captured directly from a network interface. The extracted flows are then stored as a set of features in CSV format, which can be labeled based on the type of traffic represented by the flow, either benign or some type of threat. This labeled data is then used to train machine learning models. Building on past experience, scikit-learn was used as the machine learning platform to train various models. Following in our footsteps, we chose to compare the performance of a variety of models that were used for analysis of the same data set but on a smaller scale. The algorithms used were decision tree, random forest, quadratic discriminant analysis, support vector machine, naive Bayes, and extreme gradient boosting. Of these, the decision tree algorithm produced a model that performed best overall, and the support vector machine algorithm had the slowest training and prediction times of each of these. After training our machine learning model and testing it against a subset of the CIC-IDS 2017 dataset, which produced highly accurate results, the next logical step was to test it using live data in real time. An experiment was set up to use one system as a target for testing. The system was running a modified version of CIC Flow Meter to monitor network traffic interface and examine TCP flows using the machine learning model. A second system was used as a threat simulator to attack the system using various software packages to generate data that the model was trained to recognize as threats. This testing included running simulations for GoldenEye, HALT, slow HTTP test, and slow LoRa's. The machine learning model failed to recognize threats in each of these cases, and this warrants further investigation. Moving forward, it seems beneficial to examine the use of open source network intrusion detection or prevention systems as a platform for testing real-time network traffic for threats. Such systems can be augmented to include the use of machine learning models as a means for enhancing the ability to recognize threats to the communication network. Candidate systems include Snort, Suricata, OSSEC, and Z. Such an augmentation could lead to the development of a more powerful system for quickly recognizing nefarious network activity. In short, securing modern communication networks against threats continues to be a challenge. Protecting critical infrastructure to include smart grids should be a top priority from a national security perspective. The use of machine learning models to enhance existing network intrusion detection and prevention systems can lead to more secure communication networks. More research in this area is needed in order to better protect our critical infrastructure. Thanks for listening.